Hi everyone, I'm Dr. Poe, and I just want to briefly talk to you today about the laws of thermodynamics. So we're really going to focus on the first and second laws of thermodynamics and see if we can come up with some examples that really bring those to life. So in our first law of thermodynamics, that is directly parallel to the law of conservation of mass. And the first law of thermodynamics tells us that energy is neither created or destroyed. And so what that really means for us is that it has to come from somewhere. So the energy that powers our light bulbs has to come, it doesn't just fall out of the sky, it has to come from somewhere. And similarly, the energy in our light bulb, it comes out as light, but also a little bit lost as heat. So it's all going somewhere, all the energy is accounted for. So just like we were accounting for all of the atoms on both reactants and product side when we were talking about law of conservation of mass, the energy that goes into a system, it's all going to end up somewhere. And in most cases, it's going to be light, heat, or work. So another kind of formula, if you want to think about it that way, is kind of expressed like this. So the internal energy, this change in internal energy, that is the amount of heat, which is Q, and the amount of work put in. So that's kind of like all the energy. The energy is all accounted for. It can change form like heat, light, or work, but it's all forms of energy. So just kind of keep that in mind. Second law actually has multiple parts. And so this kind of directly relates to temperature in terms of heat flow. So if you put your hand on a cold desk, your nice warm hand on a nice cool desk probably feels great, number one. And number two, you're noticing like the temperature of your hand feels cooler. So is that because the coolness is transferring from the desk into your hand, or is that because the heat from your warm hand is going into the desk? So the second law tells us about heat movements. So we know that heat, that's actually a measure of thermal energy, that's kinetic energy, that's molecules actually moving. So we know that the heat moves from hot to cold. So anything in that regard, you put your ice cube in your warm drink, the energy is going to move from the warm drink into the ice cube. It always goes from the warmer object to the cooler object. So anything related to that, that's a second law of thermodynamics kind of concept. Another is this idea of entropy, and this is everybody's favorite. I don't know if you know this, but this is about to be your favorite. Entropy, its symbol is S, just in case you need to know that. Entropy is a measurement of disorder. And I want you to think about something. And you don't have, and I'm sure this is true at some point in your life. So, the natural state of things is actually disorder. And this makes sense because if you look around your room, and if your room is like my room, it is really, really, really easy for this room to get disordered, to go crazy, to get messy. That is easy. That basically takes no energy. That's just the natural state of things. That's what's going to happen. Things are not going to naturally line up in cute little lines and little Marie Kondo boxes. It's not going to happen. The natural state of things is disorder. We have to put in a lot of energy to clean up and organize them into the beautiful boxes and the beautiful lines in the row. So, the natural tendency of things is disorder. And if you have any little kids and you put them in a nice clean room, it takes them 5 seconds to destroy it. It'll take you 5 hours to clean it. So the natural tendency of entropy is to increase in any spontaneous process. So any like sort of normal situation, disorder tends to increase. Disorder, also known as entropy, tends to increase. And that is like just so unbelievably true. It's a little painful. Okay, and so another way to think about this is when I was learning physics, there is no such thing as a perfect refrigerator. This is the last part. I hope I spelled that right. Refrigerator. Spelling doesn't count. Okay, so in related to heat and in related to disorder, so a little bit of this perfect energy in our first law, it has to go somewhere. Well, a little bit is lost as heat or as light or as something else. We're not going to be able to get 100% of the work. So that's kind of what there's no such thing as a perfect refrigerator idea really comes from, is that it's not, you're going to lose something along the way. And that's just because there's resistance in the air and there's all these other factors. So nothing's really perfect. You can't just plug in your refrigerator and have it make perfect ice cubes every single time. It's like, it's just not going to work like that. So you're going to lose some of your ability to do work to heat. So just keep that in mind. So anything involving heat movements or disorder, that's a second law kind of idea. And energy being neither created nor destroyed, that's really the first law of thermodynamics. And yeah, there is a lot of overlap between these two, but if you keep these core ideas in mind, you'll be able to think of examples that better represent one of these laws over the other. Thanks, and I hope it's been helpful.